Hi guys, Dr. B here. This is AP Chemistry topic 3.8, representations of solutions. The objective is to be able to use particulate models for mixtures, represent interactions between components, and represent concentrations of components. Intermolecular forces exist between solute particles, like we've said, between solvent particles, and between solute and solvent particles. Depending on the type of combination, these forces may either promote or prevent the formation of a solution. The tendency to mix is strong, but if the solvent-solvent and solute-solute attractions are strong compared to the solute-solvent interactions, a solution will not form. The term miscibility describes the ability of two substances to mix without separating. Similar materials are miscible in each other, or like dissolves like. Polar solvents dissolve polar solvents, and nonpolar solvents dissolve nonpolar solvents. So you can see some example of some intermolecular forces, dispersion forces, dipole-dipole, hydrogen bond, and ion dipole. Concentrated and dilute solution, so you can visibly show how a concentrated solution looks and diluted one looks. So you can see that the 0.20 molar versus the 0.1 molar, the 0.20 is more concentrated, so there are more KCl's in comparison from A to B. So according to the diagram, 0.10 molar KCl is represented with 2 potassium chloride, or 2 K plus and 2 Cl minus. That is it's 0.10 molar. So for a 0.20 molar, you have to double that. So you have to be able to represent that correctly and try to get the ions relatively in the correct sizes. Ethanol and water. What type of interaction based on their structures? So I'm going to draw out the structure for it. So we have if this is a chlorine and ethanol is C2H5OH, that means we have our if this is a carbon, we have a hydrogen here, 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 here. Then let's make this next one, since, I'll just do this. So oxygen will be this big red one. Then I'll put stripes, vertical stripes like this. So our key, that's O, carbon, H. So it's just interacting with a water. So then let's do a structure for water. So what type of interaction? So you know that this right here where I am kind of hovering over, that's your oxygen and hydrogen. So since ethanol is part hydrocarbon, the C's and H's, and part polar because the OH group, or it's also called a hydroxyl group. Since the hydrocarbon portion is small, the very polar OH group will dominate. Ethanol can therefore form hydrogen bonds with water and is considered miscible in water. So you have your negative dipole there, positive dipole. Here's your negative dipole here from the O. It's going to interact here. Your positive dipole is on this side. So this right here, that is your hydrogen bonding. Potassium chloride and water, what type of interaction based on their structures? So let's say the question is represent with 1 K plus, 1 Cl minus, and 4 waters around each of the ions. So KCl, we know, hopefully, that it's an ionic compound. The strong charges on the K plus and Cl minus would attract strongly to the polar partial charges in the water, and this is going to be called an ion-dipole interaction because the ion, the K plus and Cl minus, is interacting with the dipole from the water. KCl is therefore miscible in water. So let's try this. So let's say that when I draw this out, H2O is this, which equals that. So if you want to create a key, you have to do it and make sure it's understandable. So if I said that that triangle caret thing is my H2O, I have to know that the water molecule, the oxygen, is going to be this negative dipole, and then the hydrogen will be the positive dipole. So because the K plus is there, it's going to interact like this with the water molecules. They're going to orient themselves to where they are forming a ion dipole interaction. So the interaction is here, 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 there. Similar with water, the chloride ion, it's going to reverse. So it's going to be working out this way. Because this positive dipole here is going to interact with the negative charge from the ion. Oops. Oops. No, I didn't want to do that. Okay, cool. So what type of interaction? It is ion dipole interaction. Of the molecules above, which would form hydrogen bonds with water, which would form dipole-dipole attractions, and which would form London dispersion forces only? So hydrogen bond, remember, there should be on one molecule an H and O bonded, HN or HF. So because water is a polar molecule, we have to think about that. With its partial negative, partial positive ends, it's going to interact with some of these molecules and form hydrogen bonds. And luckily for us, since hydrogen bonding is a specific type of dipole-dipole, it should be the same answers. So hydrogen bonding. So with the negative positive dipole, look for things that have that O that's either going to be attached to an H, or you have a polar molecule, and the water will still hydrogen bond with that. So we can tell that it will definitely hydrogen bond with alcohol, because if you can just imagine like the HOH, like that. The N and H here for sure, that's some hydrogen bonding going on, so amine. But I also told you, so now if you see an oxygen like this or like this, technically that partial positive end of the water can interact with that polar end of the molecule. So ether and ketone as well. And dipole, same thing. Alcohol, amine, ether, and ketone. So then which one will have LDFs with only LDFs? So everything will form LDFs, but only LDFs with water. So that will be the alkane, because there are no polar ends. It's only just a bunch of carbons and hydrogens. Draw particulate models of two alkane molecules. So that's this one right here. They draw how the strongest intermolecular force acts between them what are the names of the force. So just so you know, you have two alkane molecules, a bunch of carbons and hydrogens. These are hydrocarbons. So it's not going to be anything spectacular, maybe. So just going to be LDFs. That's the name of the force that's going to be involved. So let's see if I can draw this out. So you have your hydrogens here, 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 and just kind of replicate that again. Should be closer, sorry. So because these are all just going to be, these are just hydrocarbons, nothing special, nothing polar. Remember, LDFs are based on electron clouds or within a molecule. So you have your electron cloud here, and then here as well. So remember our little, we did the thing in class. So the way that this works, you have to think about it in a hypothetical situation. So let's say in the molecule on the right side, so this one over here, right and left, on the right side, let's say at this particular moment, there is electrons get kind of moved over to this side of the molecule. So you have this temporary dipole. So that creates a positive dipole on the other end because the electrons, let's say they're hypothetically over here. In the one on the left, what happens is that this exposure of negativity, so to speak, will repel the negative electrons in this molecule, and it will go to the other side, exposing only the protons, if you will, in the molecule on the left. So in that temporary repulsion, there is this LDF between the partial negative and partial temporary type dipoles that exist in this molecule, and then it will dissipate. All right, that's it for now. Let me know if you have any questions. Thanks, bye.